Good afternoon, everyone. Thank you for joining. Have you ever had to juggle the demands of daily operations with the imperative to modernize your infrastructure? How do you manage that balance? Today, I would like to share a story, the story of our Kubernetes journey. How we went from a few scavenged servers running in a garage to being a full-fledged, cloud-native, multi-region platform. All that while balancing day-to operations with modernization. My name is Raul Benencia. I am a site reliability engineer at ThousandEyes, part of Cisco, and this is our story. Before we deep dive, just a few quick words about ThousandEyes. ThousandEyes is a network intelligence platform. It allows you to visualize the internet. It allows you to see internet outages happening in real time. It allows you to set up tests, monitor your own services in pretty much every layer of the network. To the end of our talk, ThousandEyes is a SaaS offering. Our early infrastructure was quite humble. We literally had some scavenged servers from recycling bins running in a garage in Mountain View. When things became serious, we moved to a data center. By the time I joined the company, we were running in 4 racks, 10 servers, virtual machines, physical firewalls and load balancers. I would say a classic baremetal infrastructure for that time. And we were already having scalability issues. So we needed to understand how could we grow faster. That's when Kubernetes came into the picture for us. And the year was 2015. And to be honest, Kubernetes was just released as stable, and we didn't know if it was going to live up to the hype. It clearly did, otherwise I wouldn't be here. But back then, we were not so sure. So that's how our journey begins. The year was 2015, and we bootstrapped our first cluster. Our first cluster was running Kubernetes version 1.1.2. And to put things in perspective, not even deployments existed. So the way we have to deploy our workloads was by directly pushing our replica sets. The cluster was running on top of Core OS, and it was configured using Ansible and Cloud Inits. We named it K1, where K stands for Kubernetes, and 1 for the amount of time that we took naming the cluster. And we hosted absolutely everything in our data center. The CI pipeline, the Docker registry, the etcd cluster, which is the backend data store of Kubernetes, and the Kubernetes control plane, of course, and the Kubernetes workers. The etcd cluster and the control plane were VMs, were virtual machines, and the Kubernetes workers were baremetal machines. Our company was running its stack on VMs, and we switched to containers. We containerized everything. I will not deep dive into this because it's a topic of 8 years ago, but it was a successful migration to Kubernetes. Everything was running. Everything that was a huge monolithic thing was now running on Kubernetes, and that's how our journey began. When we were bootstrapping the new workers, not only Kubernetes workers, but any Kubernetes server, we started doing those things manually, but of course we wanted to add some automation. So we developed a homegrown tool. We named it Shoelaces. And the way it worked was you will hook it up with your DHCP server. It will send some attributes, some URLs to the server, and the server itself will contact the Shoelaces server and frontend, and you will be able to use this frontend that you see in the picture to set up some parameters for your server, the operating system, or you could automate the whole thing using mappings. And this was really useful for us. Nowadays, we are entirely in the cloud, so we no longer bootstrap our servers manually. But if any of you still bootstrap your servers manually in a data center, check out the link. Maybe you will like this tool. Let's move to the next chapter of our story, the first challenge. We scale. So from 4 racks, we went to 10 racks. And we faced a few concerns. One of them was that our Kubernetes cluster was quite different from the rest of our infrastructure. Why? Because the rest of our infrastructure was running a mixture of Ubuntu configured with Puppet, whereas the Kubernetes workers were configured just with Ansible and Cloud init files. And we had a lot of configuration in Puppet, We had logging, alerting, logging into the server, a lot of configs. And we did not have the same configs in CoreOS. So that was one of the biggest disadvantages that we have. The other one was that CoreOS killer feature for us when we chose it, which was reviewing automatically on security upgrades, we did not have that feature enabled because our workloads still have some remnants of their monolithic past. So they were quite fragile to the restart, particularly if it was an unplanned restart. So that's why we were not using that feature. So CoreOS was not the right fit for us. We like CoreOS, it's just that CoreOS did not like us. And that's when we decided to switch the OS, but keep the cluster. We went for a modern infrastructure. At the time, we used the latest Ubuntu version, which at that time I think it was Ubuntu Xenial, Ubuntu 16. And that way, we aligned our Kubernetes workers with the rest of our fleet. We prepared some Puppet modules to install Kubernetes, both as a worker and as a control plane. And we ran with a few sharp edges, and we started with the migration plan. This migration was quite manual, I have to say, because we have to remove every CoreOS worker from the load balancer, then from the Kubernetes cluster, then rebootstrap the operating system using a new Ubuntu recipe, using shoelaces in this case, and then add the Ubuntu worker again to the Kubernetes cluster, and then to the load balancer, and repeat for each of the workers. And because we were still gaining some trust in Kubernetes, we were taking a long time to do this. And we will do maybe one worker every few days. So it was a very conservative migration, but it was a successful migration. It felt like we whipped the tablecloth from under the table, and our developers barely felt it. So this is what cemented our trust in Kubernetes. Let's move to the next chapter, jumping jeeps. So while we were busy managing other parts of our infrastructure because we were a small SRE team, we neglected doing versions upgrades on Kubernetes. We were stuck on Kubernetes 1.5 while 1.13 was out. So there was a huge version lag. On top of that, we were deploying our manifest to Kubernetes in a way that was not really scalable because we were using Jenkins, and Jenkins was triggered whenever there was a change in one directory on a Git repo for each of our workloads. And the tool that we were using was not robust enough, and also drift detection was very challenging. So if the cluster was running something different than what we have in the Git repos, we wouldn't know about it, and that's a big no-no. So trade-off. Do we upgrade the cluster and try to modernize it, or do we create a new cluster and migrate to it? And in this case, we decided that if we wanted to go through the upgrade path, we will have to bother our engineers and our workloads with every upgrade, every breaking change from 1.5 to 1.13. Whereas if we took the toil and started a new cluster ourselves and have it ready to be used and then migrate the workloads, we will have to bother our developers only one time. So that's what we did. That's what we did. And this is how a new cluster emerged. We set it up using Kubernetes 1.15, also running in Ubuntu, also managed by Puppet, albeit a newer, more modern version. We name it K2 because when it comes to naming, we like to keep the suspense at 0. We completely remediated the drift problem by using Argo CD for deploying our manifests. This is it's a great tool. I can't stress enough how good it was for us to have this visibility because, yeah, it was really easy to see if something was out of place. So this is a tool that we still use even nowadays. So how did we do this migration? Well, because we were not that big of a company at that time, we had a manageable size of our workloads. So it was a loosely coordinated effort. Each team was in charge of migrating their own workloads because they will knew their dependencies. We didn't have any service mesh then. So dependencies were something that you could track because you knew your services very well. And they pretty much started parallel workloads on case 2. If it was a singleton service that was only able to run on a single cluster, then the service was stopped in case 1 and then started in case 2. But it was a very simple migration, I have to say. And we involved the whole team. Again, we were a smaller company back then. Let's move to the next chapter of the story, sailing to the clouds. We kept scaling. Our 10-rack data center was running small, and we were only on one region. This data center was in San Francisco. Latency was really high for our overseas customers. Particularly, we have many customers in Europe. And also, we didn't have a disaster recovery region. So everything was a single point of failure. If an asteroid hit that data center, we will be gone from the map. So we need to do something about it, and we need to move. We moved to the cloud, and our choice was AWS. Now, when we started thinking about AWS, we have to make a critical choice, which is the region that we were going to choose. And because we just wanted to shift our current workloads from data center to the cloud, we chose US West 1, which was the closest region to our data center. We connected them together using AWS Direct Connect. And yeah, we discovered a few problems along the way. First, US West 1 has, I think, only 2 availability zones, which is a problem if you want to deploy any highly available service, because usually you need at least 3 availability zones to avoid quorum and split brain situations. Second, to make it more interesting, EKS was already a thing, but it was not a thing in the region we chose. So we had another decision to make. What do we do with Kubernetes? Do we start a new cluster the way we know how to do it, but in AWS, or what? We decided to extend the cluster that was living in the data center. And we did that by initially testing this approach, preparing a few Puppet modules again with the existing code base, but with a few tweaks for AWS, and bootstrapping a few EC2 instances that will act as Kubernetes workers, that they will connect to the control plane still running in the data center. That was successful. Because these EC2 instances, maybe they need some security group to access databases, or we were not going to just run our bottles directly over there without being sure, without doing some canary testing to check that the workload really behaves the way it should. So we did some control, right? And we applied some taints on the AWS nodes. And only for workloads that we knew that they were ready to run in AWS, we will add a toleration. So to recap, in Kubernetes terms, a taint is like a node repellent that prevents pods from landing on that node unless it has the right tolerations. Let's talk a little bit about how we migrated the control plane. This was quite straightforward as well, because the only thing that we did was to bootstrap Kubernetes control plane nodes on AWS, and we configured our workers from AWS to connect to this control plane. But under the scenes, everything was connected to the backend etcd store running in the data center. And this is where the interesting part comes of this migration, because the challenge was that we only had 2 availability zones, and etcd, in order to be considered highly available, we need at least 3 zones. So we were not able to have a situation such as this one, where we just deployed nodes on 2 availability zones, because we will be exposed to split brain situations. The way we solved this was by using an availability zone from another region. And we chose US West 2 because it was the closest one to US West 1. We deployed a 5th node there. And what we ended up doing was to configure our control plane nodes, which are the ones that need to connect to etcd, to only talk with the etcd servers running in the same region in US West 1. So they were configured to talk with the first 4 etcd servers of the cluster. But the etcd cluster knew about this 5th node, and it was syncing through this 5th node in the background. And using this approach, we did not notice any latency, any extra latency. So I have to say that this approach worked really well for us, and we are quite happy with the result. We also have to migrate the workloads to AWS, and the approach we took was similar to the migration from Case 1 to Case 2, in the sense that we involved the whole engineering team for doing this. Technically, everything was still part of the same cluster, so what they had to do is to decide when they were ready to run their workloads in AWS and add the tolerations to their workloads and some node selectors to select AWS nodes over data center nodes. And that's what all they had to do. And even though this approach worked really well for us, it was not really an approach that we could keep using, because teams have their own timelines as well, right? We cannot be bothering them with infra work, right? Like where their workload needs to be running. That's a decision that maybe it's part of the SRE team and not so much of them. They just want to run their workloads. They don't really care of where it's running. Anyway, we use this approach for the migration. It worked well, but it's not a scalable approach. So it was the last time that we used it. In the meantime, while we were doing this migration, we completed it in staging, and we were about 60 or 70% done in production. There is some mid-migration fun, because AWS enabled EKS general availability in US West 1. So we had yet another trade-off to consider. Do we complete the existing migration, or do we start anew, because we knew that eventually we wanted to be in EKS? So our thought process here was, we are already done with staging. We are 60 to 70% done in production. We cannot afford to lose the environment parity between staging and production. So we decided to go ahead and continue with the migration and finish the migration. So the takeaway here is that sometimes, in the name of reliability, it makes sense to do throwaway work. Moving forward, testing new waters. In a parallel track, our small but amazing team was focusing also on our new horizons, Europe. We were addressing the latency issue that I mentioned earlier. We started something that we named the multi-region effort, and we chose EU Central 1. And this time we had 3 availability zones and full EKS support. We were new to EKS, but we had some code base already on Terraform. So we decided to bootstrap our EKS clusters using Terraform as well. We aimed for a setup where we could just create one pull request and everything was ready to be used. That was our moonshot. We didn't really get there. We needed to do some code layering because of dependencies and things living in multiple repos and using multiple technologies. But in a nutshell, we needed at least one commit to bootstrap the cluster, a separate commit, separate pull request to create some core services via Terraform as well, and then also another one for creating all the load balancers that will be in front of the EKS cluster. But overall, it was a successful launch. We named this new cluster EKS1 because, again, we like to keep our names boring. And yeah, our teams were able to easily deploy to this new cluster, and we began serving our European customers with reduced latency. It was a successful opportunity here, and it was so successful that there was a lot of demand for EKS clusters. So we had demands for disaster recovery, maybe team-specific clusters, tool-specific clusters, and we have to tweak our modules to make them better, more reliable, faster. And each cluster that we bootstrap, it improved the process a little bit. However, despite all this amazing uniformity, one cluster remained the exception. And if you have been paying attention, you know that this cluster, this sinking ship, it's K2, which was, in other words, our flagship cluster, because it was the cluster serving our US customers, which is, it was our main region. Because our small team was focusing on developing these EKS modules, making EKS amazing, K2 maintenance became something of a secondary thing, leading to a lot of version lag. However, we were able to keep a consistent upgrade schedule on EKS. So you can imagine that there was a huge, huge version drift between the manifest of K2 and the manifest of EKS1, because we were running the same workloads pretty much, just in different regions. So how did we address these inconsistencies? Well, we use Customize for this. Customize provides functionality for doing patches directly from YAML, from the customization.yaml file. And here in the example, you can see how we are upgrading an API version from beta to the new one. So, of course, this was a solution. It was a good solution, but it's not something that we really wanted to have in our code base. These were tactical situations that we used, but strategically, we needed to move to EKS, so we have all our infrastructure running in the same version. On top of that, to make matters more interesting, more spicy, our K2 cluster, which was an old beast, was facing a hard limit of 255 nodes. And we were nearing capacity. We were over 200 nodes. And yes, we could have fixed this. There are many workarounds that we could have applied. But we wanted our focus and our effort to be focused on the migration, not in doing throwaway work. Of course, I mean, if we have reached this critical situation, we wouldn't let our customers be affected by it, and we will have worked on a solution, on a tactic solution. But we decided to put all our energy in the migration, which leads to the last chapter of our story, the gangway. So we knew that we wanted to migrate from K2 to EKS1. How do we design this migration? We could not use the same approach that we used from K1 to K2 or from K2 to AWS, because the company grew. It grew a lot. We were running hundreds of workloads. We had dozens of teams. And more importantly, there were many dependencies between each of the services that it was not really clear what depended on what, okay? So we need a different approach to avoid a migration nightmare. What did we do? We took this as an opportunity to implement a service mesh, because we have research into service mesh in the past, but we always lacked the right excuse to implement it, right? We could always work around whatever shiny feature a service mesh will provide to us by installing yet another tool. So there was not a fundamental reason to have a service mesh. But this was it, because in a service mesh, no matter where the workload is running, no matter which cluster it's running on, services are going to be able to communicate with each other. So we chose Istio for its maturity, its community support, and we installed it in K2. We also bootstrap a new EKS cluster, EKS1, in the same region. And this is not to be confused with the EKS1 running in Europe. They are named the same, but they are on different regions. And we also bridged these clusters using an Istio east-west gateway, acting as a sort of gangway between these two very different vessels. We enable Istio across the workloads because it's not enough to just install Istio on the clusters. You also need to enable it on each of the workloads. And you do that by adding a label in the namespace and then rolling restart all the workloads of the service. So we have to do some coordinations with the teams. We automated this, so in case of problems, we could easily roll back. And then we started parallel workloads in EKS1. Again, we coordinated a little bit with the team, asking them, hey, is it OK if this service is run on this cluster as well? We kind of got a hint of when a service was not a singleton service, because if it had at least 2 replicas, then it means that it's OK if it's running in multiple places at the same time. For services that were only running 1 replica, we coordinated that with them, but they were probably singleton services, or it was a service that had a bug, because if you want to be highly available, at least have 2 or 3 replicas. We used some traffic control features from Istio to do some traffic, to shift the traffic from one cluster to the other. So what we ended up doing, let me see if I can find the cursor, is to create some subsets of the traffic based on the network they were running on. The K2 network or the EKS1 network. They were on different VPCs. And then we added also virtual services. And with a virtual service, you can choose the weight that each cluster is going to have for serving this traffic, right? So normally we went from 0 to 100 in small services, but on the services that were critical, that maybe they were the services that were connected directly to the load balancer, we use a canary approach, 1%, 5%, 10%. And this was a good choice. I think this worked quite well for us. Of course, this manifests these traffic control features from Istio. We need 1 per workload, so we automated their creation. And we generated them and added them to a Git repo. The fact that they were on a Git repo and they were synchronized with Argo meant that if something went wrong and we needed to roll back, it was simply a Git revert. And yeah, this was a different migration. It was a collaborative migration because there was some loose coordination with the teams, but overall, it was done by a small team. We tried to keep parity as much as possible between station and production. Instead of doing the whole station and then the whole production, we decided to do namespace by namespace, just because it was a migration that took a long time to do because we have hundreds of workloads, right? So we will do a few namespaces per week. And then we will do these namespaces in station and then in production. And that way, we achieved the migration of hundreds of workloads across dozens of teams with limited engineering-wide involvement. And this set the stage for the final decommissioning of Case 2, which served us very well because it didn't sink in the end, and it behaved well. It didn't create any outage. So, to wrap up, our Kubernetes journey started on Case 1, an early baremetal and CoreOS-based cluster. We upgraded that cluster in place to change the operating system, switching from CoreOS to Ubuntu. Then we modernized the cluster because we lack a lot in versions, so we moved from Case 1 to Case 2. And then we needed to go to the cloud, but the region that we chose didn't have EKS, so we decided to extend Case 2 and move it to the cloud. And then once EKS was available in that region, we migrated from Case 2 to EKS 1 using a service mesh as a starting point. Then we got a myriad of EKS clusters that they are all managed uniformly thanks to our infra's code done in Terraform. And along the way, we have modernized our infra. From manually racking our Kubernetes workers, now we are using Carpenter to automatically bootstrap nodes with the right size so we can bin pack our pods into the nodes. We are using KEDA, which is paramount for event-based horizontal auto-scaling. During our work at ThousandEyes, we have had many outages, many incidents where the fix was, hey, let's scale this service. And this really, it should be done automatically. So with KEDA, we can enable features such as scaling based on the load that a Kafka topic has, for example. We're using Gatekeeper for OPA policies, which are very diverse. You can use a programming language to tweak, to define your own policies. For example, we use one to block the creation of load balancers, of load balancer services, which we consider a security risk. And then our hopeful future. We want to fine-tune our service mesh because right now every service can communicate with every service, and that's not really necessary. It makes running Istio really expensive because it needs to calculate a lot of routes, and then you need a lot of pods for running Istio-D. And then our dream for one-click cluster provisioning is still there, and we're still working on it. We're exploring different approaches for coordinating multiple pull requests on multiple platforms. We'll get there. And yeah, we also share with you the challenges we faced as a small team and how we did the migrations at small scale and also at large scale. And we also learn how to navigate operations with sustainable practices. It's important to modernize the clusters, but let's not forget about keeping the lights on. Also, regarding managed clusters, they are not a panacea. They are not a cure-all, okay? They are amazing for bootstrapping, for ramping up the cluster, but then the manifests that you run in these clusters, they still need to be managed by you. And on a small company, it's okay if every engineer knows about API versions and Kubernetes internals. But in large environments, it's too expensive that everyone knows that they need to be running a beta version instead of the alpha version, right? So you will need a sort of dedicated team that takes care of that. And of course, automate. Automation in this case is a must to reduce human error and also to achieve speed and streamline the operation. So we have adapted our strategies to the organization's maturity and resources. We have made our decisions based on the size of our workloads and also on the diversity of our workloads. And we have always embraced continuous learning. And whenever possible, we did our incremental improvements. We keep learning, improving, and advancing, cluster by cluster. This was our Kubernetes story. Thank you so much for listening.